Welcome to this NASA professional development session. And I want to thank the 412 Test Wing for the invitation and collaboration. It is great to be part of this amazing event.
Ignition sequence start. All engines are running.
We have taken tremendous steps.
We choose to go to the moon before this decade is out.
We have achieved the earth-shaking, the breathtaking, the groundbreaking,
One small step for man.
and left a mark in the heavens. Our successes build one upon another and amplify what is possible.
The dawn of Orion.
It's time we take the next great leap. We're building the next chapter of American exploration, returning to the moon to stay, so we can go beyond to Mars, to expand what's possible and further our understanding. The architecture for these missions is already taking shape. We will go with new systems, bold designs, and a sustainable mission. You can hear it, taste it, touch it. We are going. We are training, testing, pressing our pioneering spirit into every component, defining our resolve with every line of code, and securing our success with every welcomed partnership. This is not hypothetical. This is not about flags and footprints. This is about sustainable science
Recording in
and
progress.
feeding forward the advance of the human spirit. Because we are the pioneers, the star sailors, the thinkers, the visionaries, the doers. And because we stand on the shoulders of giants to go farther than humanity has ever been, we will add our names to the rolls of the greatest adventurers in history. Every day, every mission, we advance this calling. We are NASA. And after 60 years, we're just getting started.
Welcome, everybody. Good evening. Yes, we are NASA. And my name is Monique Uribe. I'm the APDC specialist for Armstrong Flight Research Center located at Edwards Air Force Base at Southern California. And my colleague, Sara Torres, we're going to be co-hosting this amazing opportunity to be part of this event. And Sara is from Ames Research Center located in Northern California. We both belong to two of the four centers of specializing in aeronautics from NASA. So welcome to this webinar. Today, what we're going to be doing, we're going to explore, let's see. Okay, explains, and specifically we're going to be focused on the X-57 Maxwell and the X-59, the new X-planes, and we're going to see why we call it X-planes, why the X prior to the planes. As well, we're going to explore aeronautics activities and NASA STEM resources. We will share it with you. But NASA's journeys have propelled technological breakthroughs, pushed the frontiers of scientific research, and expanded our understanding of the universe. These accomplishments and those to come share a common genesis: education in science, technology, engineering, and mathematics. That's means STEM. In NASA STEM engagement, we deliver tools for the students and educators to learn and succeed. We seek to create an opportunity for a diverse set of students to contribute to NASA's work in exploration and discovery. We seek to build a diverse future of STEM workforce by engaging students in authentic learning experiences with NASA's people, content, and facilities, and attract diverse groups of students to STEM through learning opportunities that sparks interest and provide connections to NASA's missions and work. And when we talk about working with the students, we will present all the NASA activities, our next gen STEM activities, and they are connected or with next generation science standards, which are the three distinct and equally important dimensions to learning science. So these dimensions are combined to form each standard or performance expectations, and each dimension works with the order to help support build cohesive understanding of science over time. And the mathematics standards, common core mathematics standards as well. So these three next generation science standards are the cross-cutting concepts, the science and engineering practices, and the disciplinary core ideas. But how to bring or what to bring the instructional strategy for integrating STEM? Well, first of all, what is a STEM, right? STEM is a cluster of careers in the fields of mathematics, science, engineering, and technology. And any field or career who creates, discovers, or applies new knowledge to make life better for all. And engaging the students, we know as an educators, then is a challenge. So, and takes time for planning, but as an educator, we need to be open and include our knowledge of the students' backgrounds as their hobbies, sports, extracurricular activities, interests, etc. So our role as an educator is to motivate in real world context, inquiry-based learning, and student-centered methods of teaching, and solving engineering challenges using engineering design processes, and including an important role as a teamwork and communication between students. And we at NASA, we use the engineering design process in the majority of our challenges, or in all the, pretty much in all of activities that we have a lot of activities related to the engineering design process. We lead, we guide the students step by step, and in this amazing process of learning. But helping students make sense of the world using next generation science and engineering practices by inspiring the new generations. So understandings built over time. Science and engineering require both knowledge and practice. Connection to students' interests and experiences is essential. Focus on core ideas and practices, and promote equity. And when we talk about NASA, NASA is committed to promote all of these features and engage the students. But when we talk about NASA, we always think about astronauts, space, rockets. But what about aeronautics? Focusing on the first A from NASA. The first A from NASA means aeronautics, the science of travel through the air. Is more than just travel, and is more than just arriving safely to our destinations. So NASA roots go back to the National Advisory Committee for Aeronautics, or NACA, established in 1915 to supervise and direct the scientific study of the problems of flight. Some of the contributions, and we're going to be focusing today in the X-planes, and some of the X-planes are here in the screen. The first one is the X-1, or the first plane who break the sound barrier. The second one is the X-57 Maxwell experimental aircraft being developed by NASA, intended to demonstrate technologies to reduce fuel use, emissions, and noise. And the X-59, the quiet supersonic technology, intended to demonstrate technology to reduce the sonic boom. But what is an X-plane? So let's, why? And let's find why we call it X-planes. I don't know. Let's figure it out.
It's one small step for man, one giant leap for mankind.
History is about to repeat itself. Over the past 7 decades, The nation's best minds in aviation have designed, built, and flown a series of experimental airplanes to test the latest imaginative and cutting-edge ideas related to flight. Short wings, long wings, delta-shaped wings, forward-swept wings, scissor wings, big tails, no tails, high speed, low speed. Individually, each of these pioneering aircraft has its own story of triumph and setback. Together, they are known as X-planes.
Each of those X-planes has an interesting story all of its own. They've all made an incredible contribution to our understanding of flight. And X-planes are really cool.
On October 14, 1947, Air Force Captain Chuck Yeager climbed into the bright orange, glamorous Glennis and flew the X-1 into its moment in history. The Bell X-1 was the first plane to fly faster than the speed of sound, thus breaking the sound barrier. Perhaps of all the X-planes NASA has been associated with, none was more cutting edge and became more famous than the X-15 rocket plane.
The X-1, it's the most famous because it was the first to go supersonic. But the X-15, it was the most productive of our X-plane programs.
Flown between 1959 and 1968, the winged X-15 reached beyond the edge of space at hypersonic speeds, trailblazing design concepts that contributed to the development of the Mercury, Gemini, and Apollo-piloted spaceflight programs.
That's one small step for man, one giant leap for mankind.
History is about to repeat itself again, and humans will take another giant leap. NASA is building a new generation of X-planes. The first all-electric aircraft, the X-57, will increase fuel efficiency, significantly reduce carbon emissions, and reduce unwanted noises. The newest X-plane, the X-59, will be an aircraft that flies at supersonic speed. But instead of creating the annoying sonic boom, creates a quiet sonic thump.
The X-59 aircraft is an exciting addition to a long history of X airplanes, including the X-1 and the X-15. NASA is working with Lockheed Martin to design, build, and flight test the X-59 aircraft. It's going to be about 97 feet long, fly at a Mach number of about 1.42, which is roughly around 900 miles an hour. It's got a long nose, engine on top, highly swept wings, and a very carefully shaped fuselage to enable that low boom flight that we require for this airplane. There's really three phases on the low boom flight demonstration mission. The first one is we need to make sure that the airplane is safe to fly and to fly in the United States airspace system at about 55,000 feet. Second of all, we need to do validation flights to show that the airplane can fly in a variety of flight conditions and atmospheric conditions. And then the third phase is really this community response data where we go out and get the data and provide this data to regulatory agencies such as the FAA so that they can lift the ban on commercial supersonic flight.
The success of the X-59 could be the next giant leap for mankind here on Earth. This means one day in the not too distant future, you may be flying on a supersonic commercial flight over land, getting where you need to go in half the time. How cool is that? Remember, NASA is with you when you fly.
All right, thank you, Monica. That was such a really neat video to watch. So let's take a look at experimental planes historically. So on December 17th, 1903, in Kitty Hawk, North Carolina, the Wright Flyer became the first powered heavier than air machine to achieve controlled sustained flight with a pilot aboard. Between 1899 and 1905, the Wright brothers conducted a program of aeronautical research and experimentation that led to the first successful powered airplane in 1903 and refined a practical flying machine 2 years later. So all successful airplanes since then have incorporated the basic design elements of the 1903 Wright Flyer. So the genius of Wilbur and Orville lay not only in the singular act of getting a flying machine into the air, but also in the approach they evolved and employed to create the technology of flight. So their method of evaluating data gathered by testing an aircraft in flight, then refining the design based on those results remains like an essential tool in aerospace research and development. Next slide, please, Monica. This is a slide where you see on the top right, you see the NACA seal or the NACA seal. So during World War I, just to give a little bit of history, American leaders were really concerned that the nation was losing its edge on, losing its edge in aviation technology to Europe. So if you guys remember Sputnik, so in 1915, the National Advisory Committee for Aeronautics, or NACA, was formed with a mission to supervise and direct the scientific study of the problems of flight with a view to their practical solution. So in 1953, around this time, actually, it was around October 14th, President Eisenhower issued an executive order approving an official seal for the NACA-2. And so the seal is a representation of the famous photograph depicting the first successful flight of an airplane. So the seal, if you look carefully, it's kind of hard to see, but it shows the first flight of the Wright brothers Kitty Hawk Flyer taking off from the launching rail on the sandy soil at the foot of Kill Devil Hill in North Carolina. So Orville Wright is lying prone on the lower wing and Wilbur Wright is running alongside just after letting go of the right tip. So again, between 1915 and 1958 or so, the NACA really published more than 16,000 reports for public use regarding aeronautical design, research, safety, and development. And in that time, it won outright or shared in like 5, I want to say, Collier trophies, and an award established in 1911. And it was presented for the greatest achievement in aeronautics in America, with respect to improving the performance, efficiency, and safety of air or space vehicles. Next slide, Monica. So some of NASA Aeronautics contributions. So of course, NASA's always working at trying to improve flight, not only for astronauts, as Monica was saying earlier, but also for commercial flights and for commercial use. So airplane builders use NASA wind tunnels to test new airplane designs. Actually, there's a pretty nice wind tunnel right across my office when we're on center. But anyway, the winglet is also something that NASA invented as well. So because before something can fly in the sky, it needs to fly on the ground. That's why we need wind tunnels to test it out. So a wind tunnel works by moving air past a stationary object, making it seem like the object is flying. So the tunnel is essentially like this giant tube with air flowing through it, and usually moved along by fans. So important studies of aircraft, spacecraft, and related components take place in the test section. And it's a narrower part of the tube where the air flows very smoothly over a test object. So this is usually like a scaled down model, but can eventually be a full-size vehicle. So during a test, wind tunnel engineers measure how the design responds in flight. So observing its stability, the aerodynamic performance, and more. So wind tunnels are are where an aircraft, gets its first safety checks before it takes to the sky. They're also where aerospace designers can confirm their design elements perform as either expected or try out brand new technology safely without, of course, endangering anyone. And then, and while spacecraft are designed to operate in space, rockets have to travel through the atmosphere to get there. So oftentimes, the most vulnerable part of the mission is that time in that it's traveling through the atmosphere. So spacecraft that return to Earth or land on other planets can also pass through an atmosphere. So NASA tests those two through their tunnels as well. Next slide, Monica, please. So this is some flight tests. You'll see NASA pilots. On the left, you have Milton O. Thompson. You have William or Bill Dana and John B. Jack McKay. They're in front of an X-15 hypersonic rocket-powered aircraft. As you may remember in the video that was the experimental plane that we got the most value probably, and the X-15 actually was flown over a period of nearly 10 years, 1959 through 1968. So the piloted X-15 set the world's unofficial speed and altitude records. So the X-15 program contributed to the development of Mercury or Gemini or Apollo piloted spacecrafts, as well as space shuttle program. And I want to say on the right, Monica, you can correct me if I'm wrong, but is that Chuck Yeager or something there to the right? Maybe Monica can correct me if I'm wrong.
Okay, no, that's Neil Armstrong.
Prior
to be an astronaut, Neil Armstrong was a test pilot.
So thank you, Monica, for that clarification. And then next slide, please. So this is the Schlieren photography, which was invented by German physicist August Toepler in 1864 to study supersonic motion. And so it's really cool to look at. It even looks like art, but NASA, scientists use it to see the pressure waves caused by a flying aircraft pushing air molecules out of the way. This shows like an Air Force test pilot school, a T-38 in a transonic state, meaning like the aircraft is transitioning from subsonic speed to supersonic. So above and beneath the aircraft, shock waves are seen starting to form. So these shock waves propagate away from the aircraft and are heard on the ground as sonic boom. So NASA researchers in California are using a modern version of the 150-year-old German photography technique to capture images of shock waves created by supersonic airplanes. So over the past 5 years, scientists from NASA's Armstrong Flight Research Center at Edwards Air Force Base and Ames Research Center at Moffett Field have teamed up to demonstrate how Schlieren imagery can be used to visualize the supersonic flow phenomena with full-scale aircraft in flight. So the results will help engineers to design a quiet supersonic transport. Although current regulations prohibit unrestricted overland supersonic flight in the United States, a clear understanding of the location and relative strength of shock waves is essential for designing future high-speed commercial aircraft. So that's the goal, is to try to make it faster, safer. Next slide, please, Monica. So as you heard in the X-plane video, X-planes are experimental aircrafts. NASA researchers are really looking for ways to improve aircraft, not to reinvent them. And Monica mentioned this earlier as she was, introducing the topic for tonight. But the X-57, which is on the right-hand side, is a small experimental airplane that's powered by electricity. It's all electric technology, and it will make really flying cleaner, quieter, and more sustainable. So electric power is efficient and reliable. Electric motors can be placed anywhere on the plane to improve efficiency. Batteries power everything from your cell phone, of course, to equipment on the International Space Station. So the X-57 uses these rechargeable lithium-ion batteries. And it uses 12 small motors located across the wing. You can see them there to really increase the airflow so that the wing produces lifts or the lift even when the aircraft is flying slowly. And Monica's going to get more into that a little bit later. And of course, Monica already mentioned the X1, the one on the top left, the kind of orangey looking one. That's the Bell one, of course, breaking supersonic or going supersonic. So let's start talking about the X-59, which is a one on the lower right hand side. So the X-59 QueSST. So this is NASA's first piloted experimental aircraft, really in decades, that will fly faster than the speed of sound over land. The X-59 will feature really innovative technology to reduce sonic sound booms to a really quiet thump. Of course, it's constructed by Lockheed Martin Aeronautics Company, and it's being I guess at the Skunk Works plant in Palmdale, California. So it's designed so that when the X-59 is designed so that when it's flying supersonic, people on the ground will hear nothing more than a sonic thump. And so, of course, once it's fully tested and pronounced safe to fly within the national airspace, it's scheduled to be done by 2023. We don't know that for sure yet. I mean, of course, dates can change, but it will begin making supersonic flights over selected communities, really to measure the residents' reactions to any noise that they might hear. So of course, this could be the next giant leap for mankind. We know that one day it could even be you flying on a supersonic commercial flight and cutting the flight travel to half the time that it normally takes. Next slide, please, Monica. So this is an image of the halfway point of the X-59, of constructing the X-59. Of course, they're going to need to enable this, in order to enable this new commercial market for faster than sound air travel over land, they're going to need to really, use the aircraft's uniquely crafted parts to really ensure that it'll reduce the disruptive sonic boom to quiet thump. So again, this is just in Monica's language, it's just a beautiful way to look at all this being constructed. So we're looking for the first flight to be soon in 2022. There's going to be a community testing to understand, the public's perception as well on the X-59 sound. That will begin in 2024, but it's going to be happening like very soon, where we do the first test flights. So next, it's next slide. Okay, so again, you can see how it's starting to take shape here, and it's a single piloted aircraft. So it'll be used to provide rulemakers and the data needed to enable, of course, this new commercial market. And so we'll see. I mean, hopefully everything will stay on track and everything will begin to take shape. But you can start seeing the shape already on the floor and see how it's starting to be built. I believe that we have a video coming up next. So hopefully you'll get a good view of what it's going to be like. Okay, so as you can see, the construction of the X-59 is awesome. So let's talk a little bit about what sonic boom is. So what is sonic boom? This is a great chart to share with your students. On the left, you see that as an aircraft travels at the speed of sound, it begins to overtake the sound waves, which pile up in front of the aircraft. So a sonic boom is a loud kind of thunder-like noise heard by a person on the ground when an aircraft flies overhead at supersonic speeds. Air reacts like a fluid to supersonic objects. So as objects are traveling through the air, the molecules are pushed aside with great force. And this force forms a shock wave, much like a wave created by the front or bow of a boat in moving water. So the shock wave forms a cone of pressurized air, and a sharp release of pressure after the buildup of a shock wave is heard as a sonic boom. So it's similar to the sharp release of pressure when a pin pops a balloon and makes that loud noise. So again, NASA is studying and testing devices that could be used on aircraft to loosen or lessen actually the noise and the window rattling effects of supersonic flight. So with the X-59, you're still going to have like these multiple shock waves because of the wings on the aircraft that create lift and the volume of the plane. But the airplane's shape is carefully tailored so that the nose of those shock waves do not combine. So engineers at NASA Armstrong are working on this, and so they're really working on trying to reduce the sound. Next slide, please. So here are some next generation science standards that are going to go along with. I believe, Monica, do you have a video for this, or?
Yes, we have a video about sonic boom, and they're good videos to engage our students, right?
NASA is working to reduce some of these unwanted noises. As a leader in aeronautics research, NASA is working to reduce the sounds produced by aircraft. The low boom flight demonstration, a NASA aeronautics mission, includes the design, building, and testing of the X-59 Quiet Supersonic Technology Aircraft, or X-59 QueSST for short. The X-59 will be able to fly at supersonic speeds, faster than the speed of sound, without producing a loud sonic boom. But what is a sonic boom? A sonic boom is the thunder-like noise a person on the ground hears when an aircraft or other type of aerospace vehicle flies overhead faster than the speed of sound, or supersonic. Picture an aircraft flying through the air. As the aircraft moves, it pushes air out of its way, continuously creating sound waves. These sound waves, or air pressure waves, move away from the aircraft in all directions at the speed of sound, like ripples that form by dropping a pebble in a pond. By increasing the aircraft speed to supersonic, or faster than the speed of sound, the air pressure waves begin to pile up ahead of the airplane and compress, forming shock waves. These are similar to waves that pile up in front of a boat as it moves through water. In the air, the shock waves will move out and away from the aircraft. This creates a sudden change in pressure. The change happens so quickly that when the energy from the shock wave reaches our ears, it's heard as a loud crack of a sonic boom. So how is NASA trying to quiet the sonic boom with the X-59? Let's find out from an X-59 NASA engineer.
Well, the X-59 is designed to generate a quiet sonic boom when it flies supersonically. Traditional airplanes that fly supersonically, such as the Concorde or military jets, develop a very loud sonic boom as they fly over the ground. It's very disturbing to people on the ground, and that's a big impediment to being able to just fly commercially all the time supersonically. So this airplane is a demonstration of a capability that we think we developed to be able to shape the airplane such that it will not generate that loud sonic boom. And so if you look at a picture of the airplane design, you'll see that unlike a normal airplane, it's very long and slender. And the reason for that is to be able to shape the volume distribution and the lift distribution over the airplane in such a way that the shocks don't all coalesce into very strong front and rear shocks that make that loud sonic boom. The airplane is designed to fly at a higher altitude for a number of reasons, one of which is the distance away from the ground reduces the noise from the sonic booms. So higher, farther away would be quieter. The other is, of course, that the airplane is designed such that the lift distribution over the airplane is what we need at a given angle of attack. And the angle of attack is the wind angle going into the airplane, how it touches the airplane. And so to get that angle correctly at the Mach number we want to fly at, puts you up at 55,000 feet, mid-50s. So the biggest challenge historically has been just in the capability of being able to analyze how the airplane is going to act. We've recently developed the tools to be able to predict how the sonic boom will be produced on the airplane and to be able to trace that to features on the airplane. And then that allows us to design the airplane like you see in the picture, the long, slender airplane that then develops the quiet sonic boom.
Thank you for watching, and don't forget to watch our next video about NASA's long history with supersonic flight.
And these videos can be found on YouTube with a quick search in case you would like access to the videos. And so this chart here is a pretty nifty chart to show students where supersonic flight is. But it's supersonic flight is one of the 4 speeds of flight. So they're called the regimes of flight. So they're subsonic, supersonic, or I guess subsonic, sonic, supersonic, and hypersonic. So as you can see, they're all different. You can see the formula for the Mach number and how it's calculated, and then you can see the value for each one. So supersonic is Mach greater than 1. Go ahead and go to the next one, Monica. I know we're running a little bit short. There you go. So here is another chart that shows the formula. So as an object moves through a gas, the gas molecules are deflected around the object. As we said earlier, the speed of the object is much less than the speed of sound of the gas. So, or it's much less than the speed of sound of gas. So the density of the gas remains constant, and the flow of gas can be described as conserving momentum and energy in the flow. So as the speed of the object increases towards the speed of sound, we must consider the compressibility effects of the gas. So the density of the gas varies locally as the gas is compressed by the object. So near and beyond the speed of sound, small disturbances in the flow are transmitted to other locations. So, as sound waves. So Monica, do you want to go on and start talking about X-57? I'm sorry, I know I took a little bit too.
No, thank you. Thank you, Sarah. You are fine. Thank you. And as you can see, aeronautics is a great opportunity to connect our students with mathematics, physics, aerodynamics, manufacturing, and trying to answer the question then some of the students are when they are in a math class. Why do we need to know mathematics, right? So, and you can adequate these activities for lower graders and upper graders. As Sarah was mentioning, the Mach angle, the formulas for trigonometry, and we're gonna go again to see one of the activities related to trigonometry today. So now we talk about the X-59. Now let's talk about the X-57 Maxwell. So this is the project. X-57 is one of the NASA's X-planes that's been experimental, because we have an X prior to the name, as experimental. So this is a small experimental airplane powered by electricity. All electric technology will make flying cleaner, quieter, and more sustainable. Why was the X-57 nicknamed the Maxwell? Well, James Clerk Maxwell, a 19th century Scottish physicist, pioneered the theory of electromagnetism, so which paved the way for Einstein's theory of special relativity and Planck's formulation of quantum mechanics. So the X-plane nicknames are proposed by the program team. The principal investigator is Sinclair, coming with the Maxwell nickname, and I think is proper and is an amazing because we have a lot of physics involved on the X-57 and pretty much on all the X planes. So we can see here in this graphic how the engineering design process is taking place. So first we have the Tecnan P2060 wing area. So the X-57 is a modification, is just the modification of the wing area. So it's produced by converting an existing generation aircraft. And the X-plane is being built by modifying the baseline Italian Tecnan P2060, so that is powered by an electric propulsion system. And how we can use this with our students? Well, compare and contrast, right? So how the area was before and now how the area is. And we can see, we can check small motors and two big motors. So two big motors called cruise motors. The two wingtips cruise motors. And we have units here, and these are important facts, and we need to share with the students, and they need to show the units. So because when we talk about numbers, we need to specify their kilograms, horsepowers, or miles per hour, etc. So how can a small wing act bigger? Well, the X-57 aircraft uses 12 small motors located across the wing to increase airflow so that the wing produces lift even when the aircraft is flying slowly. And two big motors called the cruise motors. So, but let's watch a short video about the X-57 unique wings. Yes, flight NASA. So we need to talk to the students about the four forces of flight and Newton's law. But in relation with the X-57, so is environmental friendly. So how does distributed electric propulsion technology stack up? So we are creating a cleaner, greener, and cheaper aircraft or airplane. So for the X-57, we talk about the modification, right? As a small experimental airplane powered by electricity. So we are working with a modification on the wings. And the NASA seeks objective for these modifications for 4 primary and 2 secondary objectives. Modification 1. So the first phase of the X-57 mission tested the potential for electric propulsion. So we are talking about electricity now, right? So we can talk about batteries with our students as well. So principles of how the battery works. So we're gonna show you some NASA activities connected to how to build your own battery. So the LEAP tech ground tests were conducted on the lake bed outside NASA Armstrong Flight Research Center, Mission Directorate in California. Mission 1 is completed. goal was establish baseline TechNAM performance and the test pilot familiarity around with a truck to high speed. So mission mode 1 is completed. Modification 2 or mode 2 is happening right now. So the second phase includes both ground and flight test. Electric motors, batteries, and instrumentation are some of the technologies being tested in this section. A new wing design to accommodate 2 new engines has also been developed, but is not yet flown on the X-57 at this stage. So goals: establish electric power system safely, establish electric TechNAM, retrofit baseline. Modification 2 includes, this is an example of how we can bring the electric system to our students, how we can work with circuits, right? How we can show the application, real world application connections to real world of these circuits. This is the power distribution system, mode 2 and mode 4. It will difference. This is just one. So modification 2 and 4, we will have extra 12 motors on the circuit. So modification 3 or mode 3, the new wing designed to reposition motors is a part of the third phase. This phase, which overlaps with modification 2 and 4, also includes building and testing additional components for the final version of the X-57. The goal of this mode 3, is to demonstrate high-speed cruise efficiency. Modification 4, actually you can see it here. So modification 4 is just adding the small motors, and flight tests that include all 14 motors are the major part of the final phase of testing. Goals is to test the acoustic testing, low speed control robustness, and certification basis of technologies. That's how the modification 4 works. When we talk about engineering design process and we would talk about designs, and when we talk about aeronautics, we need to talk about engines, right? So for this specific X-57, no fuel, no combustion engines, is powered 100% by batteries. So by a cutting-edge distributed electric propulsion system, electric motors are smaller, quieter, and lighter, but transfer less power than combustion engines. So the X-57 has 14 electric motors instead of 2 piston engines. So 2 wingtip cruise motors, and the if you can see in the lower left graphic, they're retractable motors, and will be supporting the 2 big motors or 2 cruise motors when they fly. So can batteries power an airplane? This is a good question for your students or for our students. So can batteries power an airplane? Yes, yes, we can. So when batteries are charged, electrical energy is converted to stored chemical energy. So we are now talking about energy, right? And how the transfer of energy is being successful. So when a circuit is completed, the electrical energy is released for use and the battery loses charge. So these are going to be commercial lithium ion in 2 400-pound packs placed inside the custom designed battery packs, then located in the cabin, supplies 23 kilowatts hours of energy, and they are extensively tested for safety, energy uses, and weight. So these batteries have been tested because for NASA, safety comes first. So how to bring aeronautics into the classroom? So let's explore it. First of all, we need to talk to the students about the 4 forces of flight, just to provide them a background about why we need to know what forces are acting in our airplane or in our aircraft, right? Because everything has to be in balance. Including here, we can see mathematical symbols, which is lift is greater than weight, the plane races. What happens if we have unbalanced forces of flight? So for the first activity that we're sharing with you today, the name of this activity is Shape Your Flight. Is is applying, so students will be in a paper airplane and calculate the triangular area of the wings, then test and calculate the accuracy of their aircraft flight. Actually, the students will build or will use origami to construct the airplane. Then they will calculate the area of the wings, then they draw the airplane and they will calculate the area of the flight. Less area, best accuracy. So that we are related to the next generation science standard, Common Core Math standards, and the materials use paper, tape. You can see the materials here, paper, tape, ruler, pencil, and a calculator, because we are going to be using some of the areas and some of the Pythagorean theorem for upper graders. So the first step on this activity is they have to use origami to build the airplane, and the steps are presented in this, provided in this activity. Then the students will come up with aircraft or airplane, paper airplane, and they explore the geometry and its relation to aircraft designs by calculating the area of every single part of the wings. So that's mean 4 triangles. And they will find A, B, and C, and then they will use it to calculate the area of these triangles. Don't forget to talk about the 4 forces of flight in an airplane, which is lift, weight, drag, and thrust. They're opposite, they're calling the pair forces, thrust and drag, but they have to be in balance, and lift and weight, they have to be in balance. As well, we have the opportunity to talk about the geometry. How important is geometry when designing an airplane, and the Bernoulli's principle, right? The principles of hydrodynamics when we design an airplane. So once we have a background of this information with the students, we can start working with calculating the area, triangle 1, triangle 2, with the students. And then we need to go back and revise the Pythagorean theorem with them. What is the importance of knowing the objective for us to use the Pythagorean theorem? And there is a why. Now we are answering the questions. Why do we need mathematics in real life? In this activity, the students will take the send the airplane, the paper airplane, throughout the flight line, and then they will take the ruler and calculate. I'm gonna go to the next slide. So this is a representation of how they should calculate the area of the flight. So less area, the most accurate flight. They have to come up with some designs, some drawings, because remember, for the engineering design process, drawing is important. And if they need to redesign it, they can go back and check at the drawing and improve and test it again. So they have the opportunity to come up with 3 trials, and they have some discussion questions. And how can geometry be important when designing an aircraft? How can altering the size or shape of the wing design affect the flight path? And they can compare your flight triangles, which trial was the most accurate and why. So when we talk about these X-59 activities, we have these other activities related to X-59, sound effects. So the students will build a simulation of the 2 engines on an airplane. Fantastic forces. The students will work with the 4 forces of flight and demonstrate how important are they. 3 to 1 takeoff in simple and complex version. The students will be able to fly an aircraft and calculate the distance. And the X-Plane glider design challenge, this is an engineering design process design challenge. But when we talk about the X-57, we are going to talk specifically about the X-57 scratch coding activity, where the students will use a Scratch or a Snap or another programming language to create a model of the X-57's multiple propeller designs. The activity engages students in computational thinking, problem solving, and real-world applications for mathematics. Educators, well, there is a background for you to go and start with the history of X-planes, and this is how the activity is presented. The materials is the computer or tablet. Then you have to be able to download some images, and you have to create an account either in a Scratch or a Snap. So coding activity flies to download the cruise propeller sprite, the high lift propeller folder, and the high lift propeller unfolded sprite. So there is a plan that as an educator, they providing these activities, providing you with a plan, be used to introduce the students to coding or as an enrichment activity after the students have learned about the various coding blocks. And if you can see, it's guiding you step by step what they have to do. And this coding has 4 parts actually, and we are going to, you can cover these 4 parts. I don't think you can complete this activity in one day, but that's why they're providing you with all the step by step. So on part 1, so setting up the graphics, right? You need to download all the files and setting up the graphics in your computer or tablet, then defining the variables. You guide the students for this with 5 different variables, and you need to click code tab near to the in the screen, and then you need to select the variables and you will need to use for this activity. And then on part 3 is the programming, is the fun part, right? We're going to start programming, and the part number 4 is when you're going to test the code. And how you test the code? Well, and once the students are ready to test the code, you're gonna just run the program, and you need to check if the activity will work properly. So this is how you test the code. So, and there is more activities related to X-57, educator and student activity guides. There's lesson 1, construct a battery, digitally test portable electric device, physics of flight, and teamwork and project skills. I want to share with you more NASA resources. So NASA Aeronautics educational resources are here. They're free for you. And NASA Express emails, please subscribe to NASA Express, and you will have you will receive emails with all the activities and related to NASA. As well, we can start talking with our students about internships, NASA internships and scholarships. So, so spring 2022 application deadline is November 5th, 2021. And if you want to join us with digital badging, it's for free. Go to NASA APDC website, click in digital badging, and select there is so many badges, and they're free for you. Just create an account. It is important you create an account using just one email. And this is, for example, one aeronautics educator badge explains to a space flight. And this is gonna give you 7 hours for continuing education credits. As well, we have APDC webinars. Just check the APDC website. NASA resources, more NASA resources. If your students love to draw, you can go to nasa.gov, Artemis, how to draw Artemis. You can draw Artemis, you can draw the space shuttles, and you can follow in Unity and Perseverance in live. So go to Mars 2020, follow Perseverance and SpaceX Dock Simulator and Orbital Docking Simulator, as these are video games, educational video games for your students. Additional resources for you. Everything is for free. And if you need anything else, just please send us an email. We are going to be glad to support events and to support your classes. And thank you for this opportunity to share these amazing resources that NASA has for you. It was a pleasure for us to be here.
Thanks, Monica.
Is she done?